Okay, great. So my name is Mike Bauer. I'm talking about the state of Legion today. And first off, I'll say if you guys have questions or want to ask comment or make comments or questions during the talk, just go ahead and raise your hand and interrupt me. Uh, you know, I don't need to wait till the end to ask questions and talk about stuff. So yeah, so let's talk about Legion. So I'm gonna show the slide again that Alex just showed, mainly to emphasize one point, which is that there are lots of things that sit on top of Legion. And I'm constantly in an effort to try and balance, competing concerns from lots of different people. And I know I talked to a lot of you guys, in different formats and contexts and stuff like that. But just keep in mind that oftentimes I'm balancing competing concerns from different people that from all the different things that are sitting on top of Legion. So sometimes you might not always get your way, but I do try to make sure that everybody gets something they need to get what they need done. So just keep that in mind, when talking to me about Legion features and stuff like that. Okay, so let's do the first part. Something that first thing about Legion that we haven't. This will be the most painful part of the talk because we haven't made a lot of progress in documentation. So we've got a Legion manual. We had that 2 years ago, and we haven't really updated since. And so I think it might be time to start, adding some stuff to it. One thing that I've gotten a lot of requests for, which I have started working on, I was hoping to have it ready for the retreat here, but I didn't quite get it done yet, was a comprehensive guide to how to write a Legion mapper. This sort of been the most requested feature that I've gotten a lot of different from lots of different people. Sort of asking, what are all the mapper calls? What are all the knobs and stuff that you can turn? And so I've started working on this. It's going to have detailed descriptions of all the different parts of the Legion mapper and how you would write one. And so that's sort of our next step in documentation is what I'm working on right now. But if there are other things that people think that that are important for documentation, I'd be interested in hearing about those. So if you guys think of things that you'd like to hear, please let me know because this is one thing that we do need to work on, I think, a little bit more. And Alex and I have definitely fallen off the ball on this one, and we can get back on that hopefully soon. All right, so now to something a little bit more celebratory. So we finally merged the control application branch this year after 7 years. Yeah, thank you. Yeah. So it took an extra year. So if you guys were here 2 years ago, you would have remembered that I would have said it would have been done in January of 2023, and we didn't quite meet that. It took us about another year to February of 2024. But it did come with some good things, right? It comes with a new equivalent set refinement, sort of mechanism and heuristic that, was necessary to work well with control application. It also comes with some nice features like, effectively, in addition to control replication of tasks, you can also do normal replication of leaf tasks, which means that like if you want to actually run the same computation multiple times in different places to generate the same data in different places, right? You can actually do that with the mapper now. You can effectively say like run two copies of a task, maybe like one on the CPU and one on the GPU, in order to produce the same data on both sides of the PCI bus. So you don't have to copy that data over the PCI bus. Sometimes it's faster just to like compute something twice rather than move data. So you can actually do that now. That came with the control application branch. So I'll advertise that out there in case folks are interested in trying to do that in their mappers. But that did come with the control application branch. But yeah, so we finally got that merged and delivered on that aspect. Okay, so some other things we've been doing, trying to make Legion more robust. Legion is dependent on by lots of different people and lots of different contexts, and so it's very important that we actually make it correct. And I think we've taken a lot of really good steps in the past 2 years to really make this much better. So the first thing that we've done a lot of is improving Legion Spy verification. So Legion Spy, is our tool that we do formal verification of Legion runtime, checking to make sure that it's actually computing dependencies correctly and maintaining coherence and the sequential semantics of your code. Right. And we've done a lot to make Legion Spy more robust, check more things. Right? It checks things like use after free and physical instances and atomic coherence and all sorts of parts of Legion that it didn't check before. It also does checking on multi-node and it always did checking on single node execution. And we now have multi-node execution, verification in our CI jobs. And so every Legion pipeline that runs, does a little bit of multi-node verification of the Legion runtime to check to make sure that we're not breaking stuff. So we've definitely taken some good steps on that front to improve things. And then there's a little bit of advertisement for Elliot's talk tomorrow, but we now fuzz Legion's logical and physical analysis dependence analysis stages, effectively generating all sorts of interesting combinations of data usage and privileges and regions and fields and stuff to try and really exercise Legion's dependence analysis and coherence analysis. And so I'm gonna let Elliot talk more about that now or tomorrow, but we do this periodically. So I do it about once a month. I run the fuzzer on stuff and see where we are. And then Elliot does it before every release. And that really has, I think, made Legion much more robust and made sure that like, we're catching lots of very interesting, very rare bugs that you wouldn't find otherwise. And so Elliot will talk more about how the fuzzer works tomorrow and actually exercises Legion in more detail. Okay, something else that we've done since the last retreat, and this is something that we promised in the last retreat too, and we've actually delivered on this one. So tracing is sort of like our way of improving, it's sort of aligning runtime analysis overhead when you're doing things repeatedly, right? Effectively being able to find commonly re-executed sets of traces or of sequences of tasks and copies and other stuff, and then replaying them much faster than you would normally, right? And it's sort of like a jitting Legion becomes more like a jitting interpreter in that mode. And so some of the things we've done to actually improve tracing, right? We now support non-idempotent traces, which means that you can sort of have tracing code mixed in with non-tracing code much easier than you used to before. So you can effectively not have to have traces that run back to back to back all the time to get really optimal performance. You can actually like do a trace and then have some non-trace code and so forth. One of the things that was requested was effectively being able to release memory when not in use. So when traces are not being replayed, they actually release the handles on their instances, which means those instances are eligible for garbage collection if you're memory constrained. And those instances will be collected, and if they are, then those traces won't be eligible for replay. But effectively, it doesn't cause you to run out of memory the way that it used to in the past. So that's been another improvement. And finally, again, on the safety feature, there are now checks that like if you say begin trace, end trace, we'll actually check that you're actually rerunning the same sequence of operations. You effectively compute a hash of all the operations and tasks that you launch, and then verify that you're actually abiding by the tracing semantics that you should be. So another feature that we've been developing, and this one isn't quite in the master branch yet, and this is thanks to work that Rohan did, is effectively support for automatic tracing. And this is shortly going to be in the master branch, and I'll tell you a little bit about why we think it should be on by default. And so automatic tracing effectively is a way to automatically infer where the traces should go, right? So today you have to sort of say where the begin and end trace, sort of markers are in your program. And this would allow you to not have to do that. In fact, like it'll allow us to find traces in programs that have repeated sequences of tasks and stuff without users having to really do anything, right? And so effectively what it does is the same sequence of hashes that we compute for safe traces, we effectively just use those as like a sequence of hashes that become a string, and then we look for like common substrings inside of that sequence, right? And it's an extremely low cost algorithm. It only takes about 5 microseconds per task launch. It doesn't interfere with explicit traces, so if you still want to mark your traces, you can still do that. And it can be disabled, but we're actually going to probably turn this on by default, just because like the benefit of tracing for folks that actually like for programs that actually can benefit from it is pretty large, right? It turns Legion from interpreter into like sort of a JIT, and makes it much more efficient at doing what it needs to do. And so probably after this next release, we're actually going to roll this out into the master branch and turn it on by default. You don't have to do anything to use it. It'll just be on there in the background. And because it's very low cost, we don't expect you to see any problems with it. But if there are traces in your program, it'll just sort of automatically find it. If you do want to turn it off, again, there's a flag that you can just turn it off with. So that'll be in a very future, very soon, very soon to be in the master branch. There's still some more things to do for tracing, trace compilation and optimization. There's lots of optimizations that we can do, on traces that we're not currently doing to try and improve them, like reusing memory to try and reduce the memory footprint of traces and stuff like that. So still needs to add some features for that. Support for predication has been requested quite a lot, so that's nearing the top of the list. And then lowering to realm graphs and ultimately to kudu graphs, to try to make the traces actually lower down onto the hardware as efficiently as possible is something else we'd like to really be able to do in the future. So there's some early work going on that front, but it's not quite ready for real time yet. Okay, another feature that we promised in our last retreat that we now have support for. It's not quite in the master branch yet, but again, it'll come after we cut this next release. It'll be in the master branch right after that. So managing memory in Legion can sometimes be a little bit tricky. There's there's 2 different stages in the pipeline where you can actually allocate execution, right? So you can allocate, and to do this, we kind of have 2 different pools today. One for managing deferred allocations, at the mapping stage of the pipeline, where you might need to make future instances or need to create instances for your regions when you map your tasks and other operations. Right. And the other pool that we have is the eager execution pool, which is for making output regions and future return values and deferred buffers and stuff like that. Right. And this is a little unfortunate because it kind of requires you to this is necessary to have these 2 separate pools of memory, because if you don't, you can actually get deferred allocation deadlocks. And I'm not going to go into the details about how you can get those deadlocks. I'm happy to talk about it offline. Just know that like, there is a case where you can get deadlocks if you don't have these two separate pools today, right? And this leads to this like sort of dreaded eager alloc percentage flag that you have to set, which kind of like cuts every memory into pieces, right? Saying like, how much of this is for the deferred pool and how much is for the eager pool. And it's really hard for users to actually set this value correctly, right? It's really unintuitive and not something that people like to think about, and it's really hard to gauge. So we want to make this much better. And so we've come up with a sort of a branch that actually fixes this. It's called the one pool branch. And the idea for one pool is to effectively not have two pools. You just have one pool, right? And it's actually going to be the deferred pool that is the one pool, right? And the idea is then, if you have to do allocations during the execution stage of the pipeline, you effectively have three different options for doing this for every task that you launch. So the first mode that we support is sort of a legacy mode for folks that don't want to like, is kind of for backwards compatibility. So people don't have to do anything, to adjust to this sort of one pool world. Right. Effectively, if you have to do an execution or an allocation during the execution stage of the pipeline, right, you may, it will effectively try to get the allocation from the deferred pool. And we will detect cases where you might encounter deadlock by doing this, right? And it will effectively say you're out of memory at that point. Our analysis for this is sound, but it's not precise. So we might say that you're out of memory when you may not be, but we guarantee that you won't deadlock, so your program won't hang. So this sort of for backwards compatibility, you're welcome to try this and use it, and it will work, correctly until it tells you you're out of memory. But otherwise, it will be pretty safe and make sure you don't have to do anything. So the second mode that you can actually do is to effectively create, for every task launch that you do at mapping time, you can effectively create these little task local pools that will be used to satisfy all the eager allocations that you have to do during the execution stage of the pipeline. And so that requires you to put sort of a bound on how big that pool is, right? You can either do it, at mapping time dynamically, or you can do it statically when you register the task variant. Effectively say, this is the size of the pool that I need to run this task in each of the different memories. You can have like different size pools. So you might have like a bigger pool for your frame buffer memory on your GPU and a smaller pool for your zero copy memory. So you can put bounds on each of those different memories and say, make these little task local pools that you use for satisfying these executions. And this way will be the fastest. It will effectively, work very efficiently, and you'll have this pool that will handle all the allocations. And so I recommend that you do use this one because it's both the safest and the fastest. But it does require you to think a little bit about how to put the bounds on those pool sizes. And again, you only need to do this if you actually do these like sort of these allocations during the execution stage of the pipeline. If your tasks don't have output regions or deferred buffers or anything, then you can just like ignore all this. But if you do have those things, you do want to think a little bit about this. And then the third mode that you can do is what we call unbounded, where effectively maybe your task, is going to produce an output region, and it's really hard to put a bound on how big that output is, right? So you can't really make one of those task local pools, right? Like you can't say how big the memory is going to be for this task as an output. Well, what you can do is you can effectively say, I'm going to make my task have an unbounded pool, right? Effectively that I'm going to need to like block off that deferred pool so I can allocate as much as I need from it, during the execution stage of the pipeline. And that will block later tasks that are coming in that need to allocate future instances or normal instances for regions and stuff. It will block them from doing those allocations until the task that has sort of grabbed this sort of unbounded privilege, has finished executing and finished doing all of its allocations. And that way, you guarantee that like, if you're really in a memory constrained regime where you're trying to squeeze as much, as trying to make sure you don't run too many things in parallel and make sure that, your problem set stays within the size of the memory. Right, it'll make sure that works correctly. It won't always be fast because it'll block some stuff at the mapping stage and possibly expose some mapping latency, but it'll still like make sure that your program will fit memory. When you do set this like unbounded, sort of output sort of condition for your task, we actually let you say three different ways that you set this unbounded sort of restriction, right? So the first one is restricted, saying like only one task can have like an unbounded privilege on this memory at a time, meaning that all other tasks are sort of blocked at the mapping stage if they need to allocate anything until the execution of this one task is done. There's another one, which is the index task scope, which effectively says that other point tasks from the same index tasks are allowed to run in parallel with, and potentially be allocating memory, out of that deferred pool at the same time. And then permissive, which says like, I actually don't care. I'm going to do unbounded, but I'm going to let other things, bypass the mapping stage and do their own allocations in parallel. And if I run out of memory, I run out of memory. Right, but effectively you can control that from your mapper. So permissive, I guess it's So what I'll say is that permissive is still won't try to do permissive still will not allow other tasks to do allocations like in their. I guess you can mix them, but if you do, so you're saying you have one task that's permissive and one task that's in like legacy mode. Oh, if everything is everything is permissive. Um, let's see. Everything is permissive. It's actually kind of legacy mode. Yes. Yeah. So like effectively that's legacy mode if you're willing to go all the way back there. Yes. Yeah. So everything can then allocate in parallel. Although let me think about one thing. I think permissive may only allow other permissives to do unbounded pool allocations at the same time. It won't allow other things to potentially be mapping in the mapping stage of the pipeline. It'll still block the mapping stage for things that are not doing unbounded pools. So it'll still be safe in that regard. Yeah. Okay. So yeah, so this change will actually, for those of you, again, I'll just emphasize this doesn't matter if your tasks don't actually do any allocations at the execution stage of the pipeline. But if you do have those, you should start thinking about how to do this. We're going to release this in the next branch of Legion. Again, you can rely on the legacy mode, so there's sort of like a smooth on ramp here. You don't have to like jump and learn all this stuff, but it will be good if you do make like deferred buffers and stuff to start thinking about how to put bounds on your outputs. Okay. Another thing that we've done since the last time, this is work that was done by Ruben Shu and Elliot. This is sort of a resilience framework for Legion that we call Relight. So Relight is a library that sits, sort of between region to Legion programs and Legion. It's sort of a drop-in replacement. It kind of like interposes itself between Legion. And the idea is that it's going to make it really easy to do checkpoint and restart for your Legion applications, right? So the way that Relight works is effectively, it interposes itself, and then you sort of say, either in your region program, you say you're going to, use Relight, or in your Legion program, you sort of use the Relight namespace instead of the Legion namespace. But then all the interfaces and stuff all remain the same. The only thing you have to do then after that is to sort of annotate where in your program you would like to take checkpoints. Sort of like add this like checkpointing intrinsic into your code. You just sort of stick it in, wherever in the sequence of tasks you want to take, checkpoint, you put one of these intrinsics in there. Right. And then what Relight does is it'll automatically figure out, which regions have to be checkpointed at that point in the program in order to be able to recover from, a fault, to that point in the program. And it will save all that out into checking the audit partitions and stuff of the regions that you've already made, figure out what fields to save and are live and need to be saved and so forth. And then, if your program crashes or if like your job, runs out of its time limit and you need to restart, from when you launch your next job, all that you do is you just, rerun your program the same as you did before. You don't have to write any special code. Relight will effectively restart your program from the beginning and does this really cool fast forward replay, effectively skipping, anywhere from 10 to 100,000 tasks per second, running all the way back up to wherever, your most recent checkpoint was. And then it'll resume execution from that checkpoint and start taking new checkpoints and so forth. And it does all this sort of transparently and automatically. And this is kind of one of the cool things that you can do with task-based programming models is that you can easily introspect your program's execution and actually build these sort of like automatic checkpoint restart frameworks. And so if you do have a need for checkpoint restart, like we have this new Relight library, definitely go check it out. It's already in the Legion repo. We definitely encourage you to try that because we think it's a really attractive way for doing this. So you don't have to write all this like custom code to do checkpoint restart with your Legion applications. Okay, some more improvements that we made. So we've done a lot of work since the last retreat on index-based task enhancements. So the first one that we've done is we've actually added support for these concurrent index-based task launches, right? And so we've noticed that lots of folks want to use collectives inside of their tasks, maybe like MPI Altol or nickel reduce, right? And using that in a task-based programming model where tasks are dynamically scheduled and reordered and all sorts of things can be kind of challenging. It's subject to deadlock. So that's the blue one and the red one, and they're each going to do a collective operation, with their own communicator, right? If my schedule looks like this, right, I'm going to hang because effectively, like, one task is going to start on processor X, and then the second one's going to be blocked waiting on that one. Right, same thing, but over here we get the dynamic scheduling of this point task, for the blue one first and the red one over here. Right, both these guys are trying to do collectives that need to synchronize with each other in sort of a cross product kind of way, and you end up blocking because nobody can synchronize and finish their collective, and they're blocking on the processor. Right, so you can very easily trip yourself up and get yourself into deadlocks. So one of the things that we've added since the last retreat right? It's effectively a way to say to Legion, I want this index-based task launch to be concurrent, meaning that all the point tasks need to map to different processors, and they all need to be able to run concurrently with each other. And they need to be ordered in such a way that, that I'll get to in just a minute, or they're able to effectively be able to have a consistent order for things that are doing concurrent things, or so you don't get deadlocks like this. And we use a dynamic protocol to guarantee this. So all you need to do is annotate your tasks, your index task launches as being concurrent, and we'll automatically make sure that it's safe to use like nickel and MPI and other collectives inside of your tests. So yeah, question. Well, that's what concurrent index-based task launches do. It guarantees that you're not going to get a deadlock like this. Um, yes, but normally, like in a normal Legion program with an index-based task, there is no guarantee of like point task being, even being scheduled in any particular way. Like each point task is sort of scheduled independently of each other, right? And so, we want that to be the default for performance reasons for most index-based task launches. But if you do need this special property, you can effectively ask for it. And it does add a little bit of overhead. There's a dynamic protocol that adds just a little bit of latency to do that, to make it safe, but it does guarantee the safety of using these kinds of collectives inside your tests. Yep. And we don't really care which collectives you use. You can use MPI, nickel, whatever you want. Like it'll work with all of them. So one other thing that we're going to be adding in the very near future is even the ability to effectively, create subsets of point tasks that have collective behavior inside your index-based task launches, right? So like maybe you're going to have like one index-based task launch. It's going to have, 2 point tasks inside of it that need to be collective, and then 2 other point tasks need to be collective, right? And they don't all need to align in the same way, right? You can have different index-based task launches with different colorings and stuff. And so that way you don't have to have like fully collective behavior across all your point tasks. Maybe you just need to do collective behavior across like subsets of point tasks inside your index-based task launch. So that'll be coming very shortly. Okay. So another index-based task enhancement. This is work that Riesel has been doing. I encourage you to find him if you want to talk with him in more detail. But effectively, it's how do you actually strip mine across index-based task launches? Right. So today, index-based task launches actually imply that there's like these big mapping dependencies, but from all the point tasks in one index-based task launch to all the point tasks in the next one. Right. So if we got a sequence of index-based task launches, right, effectively all the green point tasks need to map before all the blue point tasks to map if there's a data dependence between them. Right. And then same thing, blue, if the red point tasks depend on the blue one in any way, then all the point tasks in blue have to finish mapping before all the ones in red are able to map at all. Right. And this can create a problem, right? It doesn't allow for really memory constrained scheduling. Right. So like maybe I actually need to actually serialize the execution of these point tests, right, in such a way that maybe I need to run a sequence of red, blue, green, and then that frees up some memory that then can be used for allocating the next green point task, right? Or creating an instance for the next green task to run, right? And so you can actually, if you actually could strip mine and run these tasks in this order, right, you can actually fit your program in memory, right, in a way that you wouldn't be able to do today, right? Because today we effectively would say you'd have to map all the green point tasks and make all their instances and stuff like that, right? And so we want to actually do this sort of more memory constrained scheduling. Right, and the idea that Riesel's been working on is effectively, if you can identify where there's point-wise dependencies between these point tasks, right, and you can do that with a name-based, dependence analysis, then you don't need to actually, have these fences across all the index-based mappings, right? You can actually just have like point-wise mapping dependencies between the points in the index-based task launch, so they can map in a particular order, and then do their allocations and actually fit your program in memory. And this way, mappers can actually achieve schedules and mappings that they couldn't achieve otherwise. And so being able to detect when you can, it's actually safe to do this sort of point-wise dependence analysis is something that Riesel's been adding support for. It'll effectively allow you to get sort of more fine-grained mapping of your tasks, so you don't have to think about like mapping a whole index-based task launch before you go onto the next one. It's related to sort of like, I'll remind everyone that this is sort of related to like, we have support already today for having point-wise dependencies between, points in the same index-based task launch. It's very similar to this, but now it's applying across index-based task launches, so from one to the next one. So we're effectively going to have support for both of those things now. So you can have point-wise name-based dependencies in both scenarios. So I want to take this opportunity just to make a point and sort of like call this out as a sort of a trend that I've noticed for the group at large, and see if sort of people have different ideas about this and about what's going on and also how we might improve it. But I've noticed a trend about index-based task launches over the past few years that I wanted to call to everyone's attention. So index-based task launches are really the secret sauce of Legion. They make everything scalable, right? Like effectively, they are the way that, we actually say that, large chunks of work are being created, right? And they're necessary for making sure that things like control application, are scalable. But they only really work if they're representing computations that take significant fractions of the machine, right? Now, you don't have your every index-based task launch spanning the whole machine, but in general, your index-based task launches should sort of be scale invariant, right? They should be dependent upon things that are, independent of the scale of the machine, right? You should be making things that are you should be launching like over all of your like AMR domains or over your whole mesh or significant parts of your mesh or whatever your data structure is, right? Like you don't want to have this just being like launching index-based task launches for subsets of like the GPUs on your node or something like that. And I've seen lots of cases recently where different people in different areas, so I'm not like calling anybody out or anything, but there are lots of users who are either skipping index-based task launches or not using them when I thought that they could be used. And I'm not really sure sort of why this is happening. But I feel like it needs some investigation because it suggests that there's like some source of friction that's causing problems, for folks not being able to like, actually be able to use index-based task launches as effectively as I think they should be. And I think it is important that we actually do make sure that, index-based task launches and I say index-based task launches, I also mean other index-based operations. It's all the same. But like we try to express our programs in this sort of more compressed way, because I think that's actually, essential to what like makes Legion successful. And so, I'm not sure what's causing that, and I'd like to, investigate that. And if you guys have thoughts, I'd be interested in hearing about like, if you've encountered this problem, what was tricky for you. But yeah, so I'm just calling everyone's attention to that and like pointing out this might be something for us to look at and think about a little bit more. The one place where I haven't noticed this problem, by the way, is for Regent users, especially those that use the auto parallelizer. Right, like it just kind of works for them, and they automatically get index-based task launches out of that. And I think that's an important success story where like I feel like we do actually have a really good story for how to make it easy for folks to actually use index-based task launches all the time. So just calling that out. Okay, let's see. Some other stuff that's happening. We are trying to clean up like the Legion runtime and actually make it, make the repository a little bit cleaner. We promised we were gonna do that the last time and we didn't get to it. But we're doing lots of stuff, and I'm not going to read off all these things, other than to mention the fact that I've rewritten about 700 of the 1,200 error messages in Legion, and I'll be finishing up the rest of them here very shortly. But hopefully that'll make error messages much cleaner and nicer for everyone. And the Legion repo will get a lot cleaner once we do this. But it does mean that we need to merge all the Legion branches to avoid creating lots of like merge conflicts and stuff. So this is kind of what our roadmap looks like. Sort of. There's a big bottleneck in there, like sort of merging down all these like these branches that I've been telling you about in the talk today, down to the great refactoring, and we're trying to collapse all those things down and get them merged, and then we're going to span back out. And I'll mention, some of the just very briefly. I've already talked about improved tracing a little bit, some of the things that are going to go into there. I'll mention very briefly these last two things in my last few minutes, and then I'll wrap up. So first off, one thing that I'm planning to start doing, once we finish the great refactoring, is this thing that I call lightweight Legion. And effectively, not all applications need full multi-node Legion, and not all of them can benefit from tracing, where we can actually optimize away all of the execution of Legion. And so they still need to be kind of interpreted. You can think of like data analysis pipelines and stuff like that. But Legion should be easier to use on your laptop and stuff, and not always in a supercomputer. And so to that end, there's sort of like two optimizations that we can do to kind of make Legion work better for folks that are running in more limited scenarios where they're not actually on like a supercomputer. Right. So one is like, if you're running a supercomputer or on your desktop as opposed to a supercomputer, you don't actually need all the macro level parallelism that we give you today, right? The whole point of this dependence analysis stage here is that, effectively to create parallelism even in this mapping stage of the pipeline so that you can hide latencies of communication stuff for like the program's dependence analysis and stuff that Legion is doing, right? But if you're running on a single node, you don't really need to do that. You can sort of do in-order mapping of your tasks. Right, and you can actually skip that logical dependence analysis stage then and just do mapping in order and actually just completely eliminate this stage, and that'll cut down on some of the overhead that you might see. And there's even a further optimization that you could do, like if you're willing to run in sort of what I call a shared memory mode, where maybe you only have like one instance for a logical region. You can put it either in your CPU or your GPU, but then you don't even need to do the coherence analysis. So you can kind of cut out like half of the mapping stage of the pipeline. Right. And so for folks that actually run on like, much smaller machines, like single node, multi GPU or single node, single GPU or something like that, you might actually be able to get more efficient Legion execution out of this, even without using tracing. So I'd like to kind of cut down on some of the overheads that you might see there. And so that's sort of what the concept of lightweight Legion. Won't really matter for those of you guys that work on a supercomputer. right? Like, Legion will work the same as it always has. But for those of you that run on laptops and stuff much more frequently, might actually make it much more efficient to run Legion programs. And so I mentioned this one in the last talk, and I'm going to sort of reemphasize it here today just to remind people who are kind of working on it and thinking about it. And that is, I think there is a need for speculative execution in Legion, right? So today we have predicate execution, where you can effectively launch tasks and give them a predicate to say whether they run or not, right? Based on some predicated future value that's that might resolve later, right? But I've seen this in LANL and Leagate cases with output regions and stuff like that. And I do think we probably do want to add at some point speculative execution, right? Some API call to Legion that looks like this, right? Effectively tell Legion that you would like to do a branch based on some future value that, is a Boolean future that will resolve at some point later, right? And have Legion sort of speculatively execute one of those two branches, right? And maybe your mapper chooses, the branch prediction value that you're going to use, right? And we'll make sure it's safe for control application and stuff. The tricky part about speculative execution is what to do when you need to recover, right? And how do you actually do that recovery? Whether you've like save some state, or whether maybe you do a relight style recovery where you fast forward again from the beginning of the task. I'm not sure. Relight style recovery might be expensive. You'd have to have really good branch prediction, which if you're in like a sort of a repetitively executing sort of while true loop or something might be really easy, but in other cases might be hard. So still lots of open design decisions there, but I'm thinking about this, and if you have use cases for it, I'd be happy to hear about it. So I'll put that on everyone's radar. Okay, and I'm going to wrap up. So I think there's still lots of stuff to do in Legion. I think we spent a lot of time making Legion correct. Like Legion has lots of complex features and lots of interacting parts, right, and different things that interact in non-trivial ways, right? And we've done a lot of stuff to really make it robust and solid and correct in all the different cases, right? But I think the thing that we really are starting to spend a lot more time now is making sort of the common cases fast and easy to use, right? And I do think both those two things are important. Right. It needs to be, but performance is important to lots of folks, but it also needs to be easy to use. And I think there's still lots of things that we can do to sort of like smooth off the edges of, some of the parts of Legion's scoring model. And I think we're taking good steps to get there. Like, for example, like improvements with the tracing and the memory allocation stuff, right? It's effectively trying to like make those things easier for folks to get what they want out of Legion. And so, my question for all you guys is, what are we missing? Like, what are the things that are still left to go? And so, I'm happy to, at this point, I'm happy to take questions, but if you want to talk offline, like I'd like to hear what you think is missing and what you'd like to see added. So with that, I'll wrap up.